Hello, welcome back. We move on to the next sorting algorithm called Quicksort. So Quicksort is, as we said, it takes in the worst case order n square running time, but in the average case it's going to take order n log n. Right. So let's see how Quicksort works. And the main idea is in a Quicksort is, which is basically the most crucial factor actually, because okay, let me first say. So the main idea is about finding a pivot element in the Quicksort. So pivot element can be any element in the. So here is an example array, and the pivot element can be any element here. Okay, so the running time of a Quicksort depends crucially on which element you choose as the pivot. Okay, so pivot element, so let me just note down. So this is called as pivot element, or just we call it pivot. So finding choosing which of these numbers do you choose as the pivot is the most crucial factor which affects the running time of the Quicksort algorithm. That gives a lot of flexibility to actually the programmer to decide on what element to be chosen as pivot, and there are a lot of research etc. on identifying which element to be chosen on pivot etc. But in our case, to make our life easier and simpler to understand how Quicksort works, we are going to choose always the first element as the pivot. Okay, whatever is the first element here, we are going to choose that as the pivot. Okay, right. But we could have come up with any algorithm which we can maybe look at the entire list of numbers and decide on any of those elements to be chosen as the pivot. Okay, but we are going to choose this as the pivot element. So the first element, so 4 is the pivot element, and here is the idea of Quicksort. So what Quicksort does is, so again, to make our life easier, I'm going to work with two arrays. One is this input array and another array which is basically the output array. Okay, right. So here, so I'm going to write the next array. Okay, so this is our array. Okay, so now we have chosen 4 as the pivot element. I'm going to mark that this is the pivot element. Okay, so 4 is chosen as the pivot element. Right. Now what we do is the following. We just go through the entire array. Right? We go through the entire array, and I'm going to know, so all elements less than 4 I'm going to copy in the beginning of the array, and all elements greater than 4 I'm going to copy in the end of the array. Okay, so what I want is, I want 4 to be placed in this array such that everything less than 4 comes here and everything greater than 4 comes here. Right? So let me do that. So I'm going to come here. Okay, I see 5. Okay, so this is some let me state this thing. This is right now the Quicksort algorithm I am explaining now is kind of a very modified, simplistic version of Quicksort for our basic understanding of how Quicksort works. There is this is probably this the what I'm explaining now is highly inefficient in some sense. So we'll have to do a lot of other work to make it efficient. But let's try to understand the basic idea of Quicksort. That's our aim, right? Okay, so I see 5, and which is greater than 4, right? So I'm going to copy it to the last. Okay, then I see 2. So I'm going to go like this. That's what I'm saying. So 4 is my pivot, and if I see anything greater, I just copy it to the last. If I see anything less, I'm going to copy it to the beginning. So 2 is there. So I just copy, which is less than 4, so I copy it in the beginning. 8 is bigger, copy it here. 1 is lesser, comes here. 9 is bigger, comes here. 7 is bigger, comes here. 6 is bigger, comes here. 3 is lesser, comes there. And what is here? 4 has to be there, right? This is my 4, which was my pivot, right? Okay. How much time did it take to run this? So this took order and time, right? Because all I did is I chose a pivot and then I just went through the array like once. Okay, I just walked through the entire array and then I copied things which are less than 4 to this side and things which are greater than 4 to the right side. And this takes order and time. Okay. Now, okay. So what is good about what have we achieved by after we did this? What we have achieved now is that we have placed 4. So 4 is in the exact location where we wanted 4 to be, right? In our output array, 4 has to be here, right? Because all these numbers which are less than 4 are here, and these have to be sorted here. All numbers greater than 4 will have to be sorted here. So 4 has to be here in our output array. So we have fixed that in one swap. One walk through the entire array, we have fixed that position. Now, okay, so the ideal pivot is something which would have split this array into 2 equal halves, but that didn't happen. Okay, we didn't get equal halves. So in this case, but an ideal pivot is basically choosing the which would have been exactly middle. Okay, now once we have this, what is the next thing we are going to do? We have to now sort this part and we have to sort this part, right? And what is the idea behind that? So how do we do that? We use recursion again. We recursively call Quicksort to solve this part and call this Quicksort to solve this part. So this is a recursive version of Quicksort. Again, for implementation purpose, you will have to convert this recursive algorithm into a non-recursive method. It's clear what I'm saying? So we recursively Quicksort this and Quicksort this, and then that's it, right? Because 4 is already in place, and then you solve it here and solve it there, we are done. Okay. Now, shall we write this algorithm, or do you want to analyze this algorithm? It's running time. Okay, let's first analyze it. What could go wrong in the worst case? What could happen in the worst case is the following, right? The worst case is that both sides, so it's not equally split, it's skewed. The split is going to be skewed. Let's assume that the pivot is always going to be this side and the entire array is left here. So basically then you have to do Quicksort on n-1 elements. Okay, so that's kind of the worst case scenario. So we can draw the tree and see what happens in the worst case scenario and the non-worst case scenario. Okay, so in the worst case scenario, what can happen? So you have a tree like this, and you split, and you get the pivot comes here, 1 element, and then you have an n-1 element here. So this is an n element array. You get split it into 2 parts like this. The pivot here, so let me call it P, and n-1 element, and then you split again. P comes here, and n-2 here. How long does it continue? You finally reach an 1 element here and P here. Okay. What is the height of this tree? This is the tree, right? And the height of this tree is going to be n. Right? So this is the height. N is the height, and at each level, how much work did you have to do? At each level, you have to go through the entire array, right? That's what we did. You have to walk through the entire array, and how much time does it take for to walk through the array here? It took n time, and here it takes n-1 because we have to walk through this n-1, and here it's going to take n-2. So finally, last case, it takes 1. So this much time is taken by the Quicksort in the worst case, and this comes out to be, the summation of this, which is order of n square. Right? So this is what happens in the worst case scenario for Quicksort. Now let's look at the best case. Okay, and I also said that the worst case, so the average case of Quicksort is also going to be good, order n log n. So maybe I will kind of give you an intuition of why an average case is going to be good. So in the average case scenario, what can happen is the following. So in an average case scenario, this split is going to be equal. So let's assume that this split is equal, just like in merge sort. What happens if this split is equal? So this is n element, and this is going to be, if the split is equal, this becomes n by 2 and this becomes n by 2, and you come down like this. Finally this is n by 4, this is n by 4, you come down like this. Finally you reach one element here, right? And what is the height? The height is going to be order log n. We know this fact because it's a complete binary tree, and we want and in a complete binary tree the height is order log n. Okay, and at each level how much time does it take to run? So here it's n, right, and here it's n by 2, n by 2, so it's going to be n by 2 time here and n by 2 time here, so it's n, again here also n, so finally everywhere it's n. So at each level of the tree you take n time, and then the level is, the height is log n. So in total you're going to take n log n time, right? So this is kind of the best case scenario where it's equally split. So you have chosen the pivot such that it's equally split. That's the right. So that's kind of the beauty here. You have chosen the pivot. You have beautifully chosen the pivot to be the middle element, the exact what is called as a median element, which comes up in the middle, and then you get equal halves. And in that case, you know you're going to get n log n. Okay, but I was talking about the average case also n log n. So the thing is that, why am I saying that average case also n log n in this case? This is kind of something like in an advanced an algorithms course, you will probably see this thing, not in the algorithms course, but in an advanced course where something called as a randomized algorithms course, for example, you can study this. And the idea is that the average case is basically given, you go through all inputs, okay, and compute what is the time taken, and then you and take the average of the time taken, and you get it to be n log n. That's the average case running time. So that's kind of difficult to analyze everything, but what you can analyze is you have so in an average case setting, what you can always assume is the following. So okay, I'm going to skip a lot of details, but this is the idea. So in an average case analysis, because any input is possible in an right, and you're going to go through any input, you're going to calculate how much time it's going to take. So any input you take, right? So what you do is the following. So let's say you're going to randomly choose the pivot. The pivot is going to be randomly chosen from all these elements. Okay. So what happens in a randomly chosen situation is that the tree which you are going to get here, the tree is highly likely not to be skewed. That's the point, which for a randomly chosen pivot, this tree is it's less skewed, more balanced. Okay, this is one can argue this. You can prove it mathematically that this is going to happen. That the tree is can't get too much unbalanced. Okay, and that happens with a very, very, very low probability. An unbalanced tree happens with a very, very low probability, and therefore most trees you are going to get, for most input, most trees you're going to get a balanced tree or almost balanced tree. So balanced, so like for us the balanced tree is like of the same height everywhere, but an almost balanced tree means the height is order log n. Okay, so most trees are going to be almost balanced, or most balanced trees have height order log n. So it can be 2 log n, or maybe so like one side can be 2 log n, other side can be log n. This can happen, but it's going to be order log n, and therefore, and since each level it can be at most n steps are taken, the total running time is going to be order n log n. Okay, that's kind of the idea behind an average case analysis of Quicksort. So I hope you get what I'm trying to say. Okay, now since we have analyzed quicksort and okay, so another thing which I wanted you to observe is the fact that why is quicksort not a stable sorting? Okay, so as you can see, I mean when I copied 5 here, right? So I think there are, let's say this was also 5, okay, and I'm going to do this. Let's do this again. Okay, so we have 2 5s there, right? And I'm going to do this. So again, we have chosen 4 as the pivot, and what do we do? So 4, and then I have okay. So let me just underline the first 5, right? Okay, this has to be before this 5. That's what stable sorting is. So now I have 4 as my pivot, and I have now 5. And where do I copy 5? I'm going to copy 5 to the last end of the list, right? Okay, and that this is the underlined 5. Now already you can see that the order has been lost because this 5 is going to come somewhere here, and that order is lost. We can just continue this, and this with 2 comes here, 8 comes here, 1 comes there, 9 comes here, 5 comes here, 6 comes here, 3 comes here, and 4 comes here. Okay, this is the pivot, and you can see this 5 has lost its position, and this is a problem, right? And so therefore this is not stable. Right, this is not stable. Let's look at an example for quicksort. Let's go through the recursive depth also. So first thing, I'm going to choose 5 as the pivot because that's our assumption. We are going to always choose the leftmost element as the pivot. 5 is the pivot, and therefore what is it we are going to do? I'm going to create a new array, and I'm going to copy everything less than 5 to the left of the array and everything greater than 5 to the right of the array, okay, as they come. So 2, 10, 9, 1, 6, 7, 5. As you can see, there is another 5, and I'm going with the assumption that it's on the left side it's going to be less than or equal to the pivot, okay, and the right side is greater than, strict greater than, and left side is less than or equal to. So now you have, this is my current array, and what is it we know right now? Once after this first pass of quicksort, what do we know? We know that you can think of this array as now 2 parts, right? Everything on this part of the array is less than everything on this part of the array, right? So what is it we have to do recursively? We'll have to just basically, if I sort this side and if I sort this side, I'm done, because I know everything on this side is less than everything on this side. So all I have done is, so I have basically reduced the problem completely now. So I have to now do recursively, I'm going to do a quicksort on this side and then recursively do a quicksort on this side. So let's first do this. Now if I have to do recursively quicksort on this side, what does it have to do? I have to choose a pivot, and which is the pivot according to our notion? This is going to be our pivot. And now if I choose that pivot, again we are going to go with the procedure. So 1 comes to the left, and then 5 comes to the right, and then 2 comes here, and it's sorted. Okay. Now if this was not sorted, we would have to go, so this was the pivot, right? We would have to, if this was not sorted, we will have to sort this side also of the array also. If this was some other numbers, we will have to sort this also. But now we don't have to go further because it's already sorted. On the other hand, let's come here, which is the pivot element. We are going to choose the left side of the array always as the pivot, right? So I chose 7 as the pivot, and then therefore 6 comes on the left, then 9 comes on the right, 10 comes on the right, and then 7 comes. Okay, now this is my pivot, right? So everything on the left of 7 has now been sorted because there was just one element. On the other hand, right is not sorted. So what is it? We have to do a sort again, a quicksort again. Recursively we have to apply quicksort. Actually, we will in our program we are going to recursively apply quicksort here, but that's going to sort the sorted array and give it back to us without basically it's not making any change. Now yeah, so now I want to sort this part of the array, right? Because this part is now already sorted, so I want to sort this part of the array. And what happens? You have to choose a pivot. So 10 is chosen as the pivot here, and so you have 9, which is going to be on the left because 10 is greater than 9, and then you copy 10 there, and this is sorted. So now you have the array like this, which is a fully sorted array, right? Okay, now this is our quicksort algorithm, and let's now write the quicksort function. Yeah, okay. So this quicksort function I'm going to write, we're going to use an extra array, okay? And after we do this, we will, I'll tell you how to modify this algorithm to not include an extra array, okay? So then we will make this quicksort also into an in-place sorting algorithm. Okay. This is my function. So BR is going to be my output array, and AR is my input array, and N is the number of elements in AR. And what is it I have to do? I'm going to take the pivot, which is the pivot is going to be, okay, the first element in the array, AR of 0 is going to be my pivot. And the next thing I do is I'm going to go through every element in the array, right? Okay. Okay, so I need to do the following. I will have to keep 2 pointers because I will have to put some elements on the left and some elements on the right. So I'm going to keep 2 pointers. So so things on the left, I'll call it L, which I'm going to set it to 0, right? Because it's going to start from 0. And things on the right, I'm going to call by R, which is equal to n minus 1. Okay, because these are my 2 pointers where I'm going to fill. So this is going to keep on increasing, L keeps on increasing, and R keeps on decreasing. That's how I see it. Okay, now I'm going to write my for loop. Okay, I don't have to okay, I could have just kept I can start I from 1 if you want, right? Okay, so I'm going to start from the right, because I'm not going to look at the pivot element. I'm going to start from the next element, right? Okay. And what is it I do? I am going to do the following. I compare, right? So I just check if AR of I is less than pivot. What is it I have to do? If AR of I is less than pivot, I have to put it on the left side. So I'll copy BR of L is equal to, and then I also have to do L plus plus, right? Yeah. So let's put the brackets. On the other hand, if AR of I, so this is less than or equal to, okay, because that's our assumption we made, and else. R minus minus will be on the right. So we come from here and go from there, right? And once we have finished this for loop, where is this? I have to put the value of the pivot. Okay, it's going to be now put in I. So ith position and rth positions are now, it's going to come from this, and then they are going to collide at the blank spot where the pivot is supposed to be. So I'll just put sorry, not I, L. Okay, so L and R are going to come to the same spot. Okay, so this is a Quicksort, a version of Quicksort algorithm. Okay, so this is just one pass of the Quicksort algorithm, right? And next, what is it I have to do? We have to recursively sort this thing, which is further involved, and I have to call it. So okay, if I have to call it recursively, what is it I have to do? Let me write this. Let me just put this a little above so that I'm going to end this bracket for loop here, and then write br of L is equal to pivot, right? And then I'm going to send the two arrays there, right? So okay, so now I'm basically using br is my the input array, right? So I have to call Quicksort, and I have to call br, and how many on the left? Okay, so I have to send how many on the left side? There are L many on the left side of the array, and okay, now also we'll have to pass a new array here, right? I'm not going in, so we'll have to allocate memory for this new array, and so this recursively it's going to be sorted there. Okay, and then after it comes back, we'll have to copy it and things like that we'll have to do. I'm going to pass the address of br of L plus 1, and this will be n minus L, because okay, and also we pass another array here. So these two recursively we are going to sort the two subarrays, and then we'll have to have some function here which basically copies br dash and br double dash into one array into br and return. Okay, I'm going to skip that part. So that will give me a sorted array. This is the main idea of Quicksort. Okay, but this is not the way you're going to see the Quicksort presentation always, simply because because this is not an efficient. Quicksort is supposed to be an efficient algorithm, and this is not an efficient algorithm because it's so much extra thing of an array. And the beauty of Quicksort is no need of this. It gives me an n-log n algorithm along with it's in place. Okay, so there's no need of this extra array. That's kind of the beauty of importance of Quicksort, which we are not getting from this implementation. Okay, but the main idea for so why did I introduce this Quicksort version 0, or the basic idea? Because this captures the fundamental idea of Quicksort, of that you find out the pivot element and then you split the array into two parts. Things on the left are smaller and things on the right are larger. This is the main idea behind Quicksort. Now once you know this idea, you will have to kind of work out the technical details to fill it and make it more efficient. Right. The trick is this in Quicksort.